Hello, this is a follow-up video in for the exponential family of distributions, and we're going to run some simulations to confirm the theoretical results that we obtained earlier. And that's specifically this video here, exponential family mean and variance, where we calculated the mean and variance of the sufficient statistics for the exponential family. And after this video, we probably spent a dozen videos looking at specific distributions within the exponential family and confirming that the general theory also holds for the specific cases, the specific distributions within the exponential family. So here, this is just going to be an R program on how to simulate our results and confirm that they equal the theoretical results. And I added every distribution that we looked at in the playlist, but a few of them we're just going to go over quickly, and others we'll spend a little more time. Like the normal distribution, we're going to have a mean of a mean of 5 and a variance of 3. And we're going to do a million replications. So we're going to still store the values of our 1 million observations in a vector y. And then we're going to take the mean of y, which is going to be our simulated results, and compare it with the theoretical mean a. And that's what we do. And they're both 5, and as they should be. And then we're going to take the variance of our observations and compare it with the theoretical variance. And another sufficient statistic when we looked at the exponential family for the normal was y squared. So we simulate our data, store it in y, take the mean of y squared, and that should equal the mean squared plus the variance. And let's see what it does. And it does. They're both 28 in this case. And then the variance of y squared is equal to this quantity here. And for details, you can go to the individual video that I did on the normal distribution within the exponential family. And here is the covariance between y and y squared. And this is kind of neat. It's 2 times the mean times the variance. And I want to look at that in a little more detail. I have it commented out so it doesn't accidentally run, because when it runs with a million observations, it takes a little too much time. So let's do it with 10,000 observations and plot it. And I'll show you what's going on. And now if we were to just plot this, if I were to say that on the abscissa axis we have y, and the ordinate we have y squared, you go, oh, that's a quadratic, and you're right. But when the mean is shifted to the right and we plot the data, it's the right piece or the right part of the quadratic. And so when you fit a straight line to this, which is essentially what the covariance does, it's the linear relationship, it's going to be positive, and because it's upward right. And now if this were centered around 0, it would be an exact quadratic, and the slope of a regression line, for instance, would be 0. And if it were shifted to the left, then we'd be looking at the left piece, and that's why we'd have a negative covariance, negative correlation. And so it does make sense that 2 times the mean times the variance is the right covariance for this for the mean of our the covariance between our 2 sufficient statistics, y and y squared. Now for Bernoulli, again, we're going to assume the true p is 0.5. We're going to do 1 million replications from a Bernoulli and find the mean, the variance, and the theoretical results and simulated results are almost identical. We do it for a binomial. Assume the size of 22 and p of 0.25. 1 million reps. Find the mean and the variance of our sufficient statistic. So the mean is NP, the variance is NPQ, and they're right on top of each other. Now I'm going to post this program in the comments so you can copy and paste it into your program. And so I do it for all the distributions that we looked at, and they are right on top of each other. Oh, for the Weibull, we had, for it to fit into exponential distribution, theoretically we have to assume that that A is known, this parameter, and then it fits into the Weibull distribution. And so let's run that, see what we get. And so the mean of 2185, that's the simulated mean, and this is the theoretical mean, are really close, and the variance is close-ish, you know. So here's the chi-squared, the log normal. Now the gamma distribution, when we looked at the Exponential Family for gamma distribution, see how it fits, the sufficient statistic was log of y and y. And when we calculated the mean of the log of y, we came up with a new function called the digamma function. And so this is kind of interesting to show that it is true. So we simulated 1 million observations, alpha 5, beta 3, stored it in y. Now let's find the mean of the log of y, and it's 2.6, and the theoretical mean using the digamma function is 2.6 also, so it's right on top. Here the mean, the second sufficient statistic, y, we calculate the mean, it should be alpha times beta, because that's the mean of a gamma distribution. Now the variance of log y was the trigamma function that we did in this video on gamma, and the results are right on top of each other. The variance is this, the covariance, they're almost identical. Now beta distribution's the same thing. The multinomial, we'll do it, and then that's the last one. We'll do 1 million reps. This is a multinomial distribution with k equal 4. We're assuming capital N is 100, and so that means when we sample, one sample is, you randomly put those 100 observations into those 4 cells, and or maybe I shouldn't say observations, 100 experiments go into one of these 4 cells based on these probabilities. And then that's one observation. Then we do that for 1 million times. So we have 1 million observations of 4 cells that that add to 100 basically. So the mean of the multinomial is in pi. So you take 100 times each of these probabilities, and that's what we get here. And the simulated results are so close to the theoretical results. That's nice. And so the variance is NPQ, and their simulated results are so close to the theoretical results. Now the covariance of these, the theoretical formula is N times Pi times Pk, and that's what we get here. So the simulated results are here. Now when I calculate the theoretical results, I use the function outer, but then that kind of messes up the diagonal elements, so I had to re-put in what the diagonal element variances are, and then I printed them. And if you look at these, man, they're right on top of each other. They're almost identical. So the simulated results do equal the theoretical results. Now here I want to show the covariance between those. I mean, and having a negative covariance makes perfect sense, because if you're putting in 100 experiments, the results of 100 experiments into 4 cells, if one of those cells is tending to be bigger, that means the others have to be smaller. So it is a negative relationship there. And just for a quick plot of this, we get this. And if you look at, let's say, let's do the correlation between the second and the third, and the theoretical says it's minus 100 times 0.5 times 0.3, and that's going to be the biggest, and you can see that it's the most negatively correlated amongst the others, and that's why, because they tend to be in there. Well, anyway, that's all I have for this video. Hopefully you enjoyed it. I'll post the code in the comments, and enjoy. Thanks. Bye.